Students, I am Professor Anindo Dash. Today I will present a very beautiful problem on quantum mechanics. This is a very frequent question which has appeared in M.Sc semester 1 examination in all universities across West Bengal, like Calcutta University, Jadavpur University, Presidency University, West Bengal State University, etc. Okay, so let us ponder into the problem at first. The problem is like this. You are given a condition, commutator AB is an entity. We all know that it's AB minus BA. Now, commutator of A with commutator AB is equal to commutator of B with commutator AB. This is given. Okay. This is the condition given. Now you have to prove these two results. The first result is e to the power A multiplied by e to the power operator A multiplied by operator B into e to the power minus operator A is equal to this given term, and e to the power operator B multiplied by e to the power operator B is this term. You have to prove this. Okay. So have a look into the problem. And I think you all have understood the given condition. Commutator of A with commutator AB is equal to commutator of commutator AB with operator B. This is given. Okay. So let's proceed into the problem at first. We'll be solving problem number 1 at first. Now, you cannot solve this problem by any other method other than the unique method that I'll be applying over here. So this problem has got an unique method to solve it. Okay, so let's proceed into the problem. So at first, let us define a term. Let us define a term G lambda, which is equal to e to the power lambda A times B times e to the power minus lambda A, where A and B are operators, and operators do have their own roots. Okay. Now at first, we'll make an attempt to differentiate this. So the first order derivative of G lambda is, it will be applying the UV method. So at first, this term is going to get differentiated. It contains lambda. So e to the power mx, we all know that the differentiation is m multiplied by e to the power mx. Here m is operator A and x is lambda. Here lambda is a scalar continuous parameter. Okay. Now let's get this differentiation done at first. So it becomes commutator A, operator A multiplied by e to the power lambda A B times e to the power minus lambda A. The second term B does not contain any lambda. So it's a constant term, so it's not going to get differentiated. So we'll move on the third term. The third term is e to the power minus lambda A. So upon differentiation, we know that if we differentiate e to the power minus mx, we'll get minus m times e to the power minus mx. So what we'll get? We'll get plus e to the power lambda A B. These two terms will remain as it is, minus operator A times e to the power minus lambda operator A. Now, one thing has to be verified. You see, operator A multiplied by e to the power minus lambda A. What will you get? A times e to the power minus x. What is the expanded form of e to the power minus x? Minus x plus minus x whole square by factorial 2 plus minus x whole cube by factorial 3 and so on. We know that expansion series. So we'll apply that. So e to the power minus x. I'm sorry. We'll apply this form. Let's see. E to the power x equal to 1 plus x square by factorial 2 plus x cube by factorial 3 and so on. So this is the form. So we'll be applying this over here. We'll solve this part. We'll be solving this part. Okay. Clear? So this is 1 plus x. X is minus lambda a plus x square is minus lambda a whole square by factorial 2 plus x cube is minus lambda a whole cube by factorial 3 and so on. We applied this. Okay, fine. Let's erase this off. So what we are getting, you see, we are getting a plus minus lambda a square, multiplying, plus minus lambda whole square by factorial 2 a cube, a square multiplied by a is a cube, plus minus lambda whole cube by factorial 3 a to the power 4 and so on. Now if you take a common from right hand side, we know that for operators taking common requires the command of direction. So here we'll be taking a common from right hand side. If we do that, then what we'll get? If we take a common from right hand side, then what will we get? First term we'll get 1. For the second term we'll get minus lambda a. For the third term we'll get minus lambda a whole square by factorial 2 and so on. You take one a common, so it will become a square within the bracket. So we all know that if we are using operator algebra, then if we want to take common, then you must have the proper command of the direction. Whether I am taking common from left hand side or I am taking common from right hand side, that must be specified. So here we have taken right common. Now what is this within the parenthesis? This is nothing but e to the power minus lambda, you see. E to the power minus lambda is getting repeated over here. So this is nothing but e to the power minus lambda a multiplied by a. So we see that these two terms, they commute with each other. xy becomes yx. So they commute with each other. So these two, they will commute. So it doesn't matter whether we write xy or yx. It makes no difference since they are commuting. So these two terms can be exchanged with respect to their position. So let's proceed. We'll get a e to the power lambda a, b e to the power minus lambda a, minus, this minus comes in front, e to the power lambda a, b e to the power minus lambda a, b. Now students, please ponder over here. You'll see that this g lambda term, the function, is repeated. So one can write it in this way. I'm sorry, this term is b, not sorry, this term is a. So what we get? We get a times g lambda multiplied by minus g lambda multiplied by a. By mistake I have written b over here, that should be a. You can well understand that because a and e to the minus lambda a has exchanged their position, b has nothing to do over here. Okay. So this is the result of g1 lambda, which can be written in commutator form, a g lambda. This is the commutator of a and g lambda as per definition. So let's name this as equation number 1. Now what if we differentiate it once more? Then what will we get? We will get a is independent of lambda multiplied by g1 lambda minus g1 lambda multiplied by a. So now the commutator becomes a g1 lambda. But what is the value of g1 lambda? g1 lambda is nothing but this entire commutator. So replace it over here. So you'll get a commutator a g lambda. Equation number 2. Similarly, if we want to write g3 lambda, then what will be the result? Without doing the step anymore, we can easily show that in case of second order derivative, we have got 2 commutator brackets. In case of first order derivative, we have got a single commutator bracket. So naturally, in case of 3 commutator derivative, by induction, we will have 3 commutator brackets. So it will become a g lambda, this is the first commutator bracket, then comes a, this is the second commutator bracket, then once again comes a, this is the third commutator bracket. So this will be the result. As simple as that. Now why have we done these things? Because we can expand g lambda in terms of Maclaurin series. How? G lambda equal to summation over n equal to 0 to n equal to infinity, lambda to the power n by factorial n, gn lambda. This comes from the definition of Maclaurin series. So that can be expanded in this way. The first term is the lambda at lambda equal to 0. So what is the first term? The first term is n equal to 0. At n equal to 0, lambda to the power 0 is 1. Factorial 0 is 1. So we are left out with g0 only. Why g0 only? Because you are differentiating 0 times. That means the function returns itself. This gn lambda at lambda equal to 0 is nothing but simply gn 0. Now you understand the first term n equal to 0. At n equal to 0, lambda to the power 0 is 1. 0 factorial is 1. So this goes. And G0 lambda, what is the value of G0 lambda? That means you are not differentiating, you are differentiating 0 times. That means the function will emerge as itself only. Its own form will emerge. So you'll get G0 at G0 at lambda equal to 0. G0 lambda is G lambda. G0 0 is G0. As simple as that. So you'll get G0. The reason is G lambda 0 is nothing but G lambda itself, because we are differentiating 0 times. This is the reason. So we get G0 plus, then n equal to 1, at n equal to 1, this one lambda to the power 1 is lambda, factorial 1 is 1, so it becomes G10 plus lambda square by factorial 2, now n is 2, G20, and so on. As simple as that. Now what is the value of G0? What is the value of G0? You see, if G lambda is defined in this manner, then what should be the value of G0? At lambda equal to 0, e to the power 0 is 1 multiplied by b, so you will get b into e to the power minus 0, that is also 1. So you get b. So G0 is nothing but b. So all these G0 terms will be replaced by operator b. Any G0 term there will be replaced by operator b. Okay. So G0 is b. And what is this? This is nothing but, as per definition, it is e to the power lambda a, b, e to the power minus lambda a. So this is e to the power lambda a, b, e to the power minus lambda a. Done? Now what was asked in the question? In the question it was asked the value of e to the power a times b times e to the power minus a. That means lambda must be 1, because we have defined G lambda to be equal to e to the power lambda a, b, e to the power minus lambda a. We have defined it in this way. So obviously at lambda equal to 1, this becomes G1. This is nothing but e to the power a times b times e to the power minus a. So we will be finding the result if we put lambda equal to 1. So we will do that now. Therefore, G1 equal to e to the power a times b times e to the power minus a, that becomes b. First term is b, second term is lambda is 1, so we'll get G10. Here lambda square by 2, lambda is 1, so we'll get 1 by factorial 2, G20, and so on. Okay. Now what is the value of G1 lambda? G1 lambda is a times commutator a G lambda. So what is G10 lambda? You see, if G1 lambda is commutator a G lambda, then obviously G10 should be equal to commutator a G0, and G0 is nothing but b, so it's commutator AB. So G10 is commutator AB. What about G20? G20 will be equal to commutator of A, again commutator AB. So we'll have two commutator brackets. What is G30? We'll have three commutator brackets. As simple as that. So we'll put the results. So we'll get commutator AB for this. We'll get commutator A, commutator B for this, and so on. Okay. So get your answer. So you get your answer. And that's what has been asked to prove. I haven't written the third term. Same thing will get repeated. Lambda cube by 3 and all. We'll have 3 commutator brackets. So you can prove it very easily. So our first question is done. This is a very important question, mind it. So this is done. Now I'll move on to the second one. Our second question is e to the power A times e to the power B. Again, let us define a function f lambda to be equal to e to the power lambda A times e to the power lambda B. Now let's differentiate this f lambda once. Apply the UV method. A times e to the power lambda A, e to the power lambda B remains as it is, plus e to the power lambda A B times e to the power lambda B. Okay. Now we will do a trick over here. This step is very important. This step is very important. This step is very important. So f1 lambda is nothing but df d lambda. This is A times e to the power lambda A times e to the power lambda B plus, you see, e to the power lambda A B. Now let us include this function over here. What is this function? This function is e to the power minus lambda A times e to the power lambda A. And students, it makes no difference. This is an unitary operator. It makes no difference. Okay. This is an unit operator. It makes no difference. But what we can do is see this part is G lambda. We have already defined. See? E to the lambda A B e to the minus lambda A. This is G lambda. This is already known to us. And this part is f lambda. So you can write it in this way. A times f lambda plus g lambda times f lambda. Now you can take f lambda common. So you'll get A plus g lambda whole multiplied by f lambda. So what we get? df by f. You see, this is df lambda by d lambda. So bring f lambda over here and d lambda over there. So df by f is equal to a d lambda plus g lambda d lambda. As simple as that. Now what is dx by x? This is nothing but d ln x. So df by f is d ln f equal to a d lambda remains as it is. What is the value of g lambda? G lambda is b plus g10. G10 is nothing but the commutator AB plus lambda multiplied by g10 plus lambda square by factorial 2 multiplied by g20. G2 is 0 is nothing but this commutator. So continue. Commutator AB 1 by factorial 2 lambda d lambda plus 1 by oh no, you don't have any factorial 2 over here, so I'm sorry. Just a mistake. You just put the value of g lambda. The first term is b, second term is commutator AB. So write commutator AB. Commutator AB times lambda. Commutator AB times lambda. So commutator AB lambda d lambda. What is the next? The next is lambda square by factorial 2, lambda square by factorial 2, the two commutators. So 1 by factorial 2 lambda square d lambda and so on. Just put the result. Just substitute it. Plug in g lambda. We have plugged in g lambda. We have plugged in g lambda. We have plugged in the values. In the first time you have got b. You see, you have got b. Let me write this once more for you all, so that there is no problem. G lambda, let me write this once more. G lambda multiplied by d lambda. What is g lambda? You have got b, first term. In the second term you have got lambda times commutator AB. So lambda times commutator AB. In the third term you have got lambda square by 2 factorial 2 times the second commutator. So lambda square by factorial 2 times the second commutator. I am naming it like this for simplicity. So you have got d ln f lambda to be equal to, see, a d lambda plus b d lambda, that means a plus b whole multiplied by d lambda, first term. Second term is commutator AB lambda d lambda. The third term is 1 by factorial 2, the second commutator A, commutator AB times lambda square d lambda and so on. Now if you integrate, you will get ln f lambda to be equal to a plus b multiplied by lambda plus, this becomes lambda square by 2 upon integration, and 2 is factorial 2. This becomes lambda cube by 3. 3 times factorial 2 is 3 times factorial 2 is factorial 3. 5 into factorial 4 is factorial 5. 3 into factorial 2 is factorial 3. So it becomes lambda cube by factorial 3. The second commutator plus dot dot ln a const ln beta. Ln beta is the constant of integration. This is the constant of integration. Okay. So you have got ln f lambda to be equal to a plus b whole multiplied by lambda plus lambda square by factorial 2 commutator AB plus lambda cube by factorial 3 the second commutator dot dot ln beta. This is the constant of integration. Now what will happen at lambda equal to 0? At lambda equal to 0 you will get ln f0 to be equal to ln beta. All these terms will be reduced to 0 at lambda equal to 0. So ln f0 equal to ln beta. Now what is the value of ln f0? What is the value of ln f0? You see, you have defined f lambda to be this. So at lambda equal to 0, f0 becomes 1, e to the power 0 multiplied by e to the power 0, that is 1. So ln f0 is nothing but ln 1, which is 0. So ln beta is 0, that means beta equal to 1, that means ln beta equal to 0. So this is our result. So ln beta is 0, so it does not exist. So what becomes the value of f lambda? So therefore f lambda becomes exponential a plus b times lambda plus lambda square by factorial 2 ab plus lambda cube by factorial 3, the second commutator bracket. So this is f lambda. And in the question you are asked to find e to the power a times e to the power b, that is nothing but f1. This is nothing but f1, because at lambda equal to 1 you will have f lambda to be equal to f1 equal to e to the power a times e to the power b. So finally you will find f1. Therefore f1 equal to e to the power a times e to the power b equal to exponential a plus b. Lambda is 1. So 1 by factorial 2 ab. You have just substituted lambda equal to 1. So make all lambda to be equal to 1. So you'll get 1 by factorial 3, the second commutator bracket. And that's what you are asked. So this is very simple. This is very simple. This is very simple. So this one has also been proved. So we have proved this result and we have proved this result. Now you have got two corollaries. The second corollary you will try at home. We'll do corollary number 1 over here. You have got a to be equal to x and b to be equal to px. Then what will happen? You see, if a is x and b is px, then what is going to happen? This a is x, this b is px, this is x. So what is going to happen? In the first term we'll get b, that is nothing but px. We'll get px. In the second term we have got commutator AB, that means commutator xpx, that is nothing but IH cut. Now what will be the value of the second commutator bracket? You see, this is x and this commutator is IH cut. So inside the commutator we have a scalar constant. Inside the commutator, if we get a scalar constant, then this commutator will be 0. And if this commutator is 0, then again this is 0. So the entire commutator again becomes 0. So all the higher order commutators will become 0. So only these two terms will survive. Only these two terms will survive. So one can say that e to the power x times e to the power px times e to the power minus x is nothing but px plus IH cut. That's it. So this is the corollary of result 1. And what is the corollary of result 2? You see, again you see, this term over here is x and this term over here is px. So this term becomes x, this term becomes px, this term becomes commutator xpx, that is nothing but IH cut, and rest all the commutators will be reduced to 0 because all the higher order commutators will vanish. So we'll get e to the power x times e to the power px equal to e to the power x plus px plus IH cut by 2. So we'll have this. Only these three terms in the exponential will survive. So that's all, students. Bye bye for now.